Imagine you're hanging out with your family and friends. It's weekend time. Spring is the right season to be outside. You're really having a good time sharing and exchanging experiences. Maybe you're drinking a glass of wine, or if your favorite cocktail is available, you might be drinking that as well. And all of a sudden, you get a phone call from an unrecognized number. You pick up the phone and you hear a metal voice of an automated alert system. You know that something is happening. It's some production issue. You don't yet know how severe the case is. Is it customer facing? How long it will take you to fix it? Can you fix it? Should you fix it? But you know you are responsible for the cluster health, so you start to investigate. You open all the right dashboard to monitor the cluster health. You also open the Spark UI, and there you notice there's some failed jobs. So if one of the jobs fails, you still don't know what exactly that was. You don't know why it failed. So you start digging. While you continue digging, you realize there's actually a lot of failed tasks happened. Failed task doesn't necessarily mean failed job. It can be that multiple tasks got failed, but yet again, Spark was able to recover and finish the job successfully. It does mean something happens in the cluster that you need to figure out and get to the root cause of it. So you start digging into the logs. In the logs, you see all this read timeouts, something related to the node server, something maybe with the Azure blob not being available for some reason. And you are positive something as terrible happened, and you start blaming the public cloud. You immediately start to think, this would never happen on-prem. It's only the public cloud that makes my life a hell. But you know what? Sometimes this exceptions happens on-prem as well. It doesn't necessarily mean it relates to the storage or to the public cloud. Specifically, small file syndrome are an issue that we encounter both on-prem and in the cloud storage as well. Hi, and welcome to today's session where we're going to deep dive into the small file syndrome and why is it even a problem. So we already seen the introduction and how it can impact and how it can change and create exceptions in our logs. But we want to really understand, where does it come from? How can we mitigate? How can we detect it? And what are the different scenarios that brings that to life? And also, what are the prominent use cases that we need to be aware of in order to mitigate it in time? So this is what we're going to talk about. We're going to talk about the problem, why it happens, detection and mitigation. And at the end, we're going to see a nice demo of how picking the different file formats can really impact our query performance. So why does it even happen? Why do we have these exceptions? Why is it a problem? So in order to understand that, we need to take one step backward and look at the Apache Spark query lifecycle abstraction. Most of you already know we have this Spark driver, and in the Spark driver, we have the job that starts the whole run. And the logic is being distributed across many executors and tasks, where each task handles its own part of the storage. And when we're thinking about the storage, we really need to understand what's the difference between local storage that we might have locally on our VMs, versus the storage that we use, the object storage that exists in the cloud. So today, when we work with the cloud, storage locality is still a major part, but it highly depends on how we build the infrastructure for the data. Many cases, even with storage locality, we'll still need to do some call to the storage itself in order to bring that information and write it at the end. So how does it look like, and why does it impact our query performance? Let's take a look at Azure Data Lake Gen 2 architecture. In Azure Data Lake Gen 2, we have two different layers. The first one is the hierarchical file system, and the second one is the blob storage. So the blob storage at the bottom really helps us with the high availability, disaster recovery, data governance and management, RBAC storage, role-based access control, where we can actually control who is accessing the data, the objects, different sizes and different lifecycle and policy management. And on top of it, we have another layer of security with different authentication, performance enhancement, which means they have a caching mechanism, so they can actually already cache the data for us. We can have faster read and write for the data. And then there is the scale and cost effectiveness and all of that. In order to understand what happens when I am doing a write operation or read operation, so actually when I'm writing a file, I'm writing 3 different components. The first one is the data itself. I'm going to write some image, some text, some bytecode. The second one is expendable metadata that's going to describe what is this data all about. So it can hold properties like management, who can access it, some statistics on the data, and things like that. And the third one is a global unique identifier. And when we say global unique identifier in the world of distributed system, it's a global unique identifier for the whole distributed systems that are connected together. So having said that, it means we're creating 3 different components. So it's not only the data that I'm saving in the system, it's also the metadata on the data itself. So I will be able to access it and enforce all the different policies, and the global identifier. By the way, without the global identifier, it will be a total mess and we won't be able to find our data in the distributed data system. This is the magic behind scaling up, because then we can have multiple machines that connect together, and together gives us this scalable storage that we like to use. And this is the object storage, and this is basically how it looks like. So when my Spark executors in the task doing a read and write call, they're actually contacting using the blob storage API and going through that hierarchy and doing this hierarchy of the global identifier, metadata, can I access, am I allowed to access it? And all the way into getting into the right machine where the data is actually stored on disk. And when we're dealing with tiny files, it means we're doing multiple of these calls. So when we're running analytics, if we're running complex analytics using Spark, imagine that all the Spark executors and all the tasks are doing these calls to the storage. And we know our storage is scalable. We know our storage is highly available, but we do know that there is some time to live. There is some TTL that we can define in order to give it, in order to give our query and our API call time that defines when we want to kill it. Because when there is high pressure, high stress on the storage, it means that there's going to be kicked in some mechanism of throttling. And throttling mechanism makes sure all the queries, all the APIs called are going to get an answer, but it might take longer. So if I define my query to return the timeout to return in like 5 milliseconds or 10 milliseconds, I might not get my answer back, and then it's going to return some exception saying, this is the TTL you defined, we can't cater to it right now, and that's it, I'm going to get back an exception. And you're probably asking, so while file size matters, and how, why we should care about when we're defining our data, our distributed data when we're working with Apache Spark. Well, this is the case. If I have 1 million tiny files of 60 bytes, that equals around 0.06 gigabytes. So if I'm doing read operation, I'm looking at around 1 million RPC, return procedure calls, that I'm doing inside my distributed data. At least, right? Because we mentioned there are 3 different components that we create when we're when we're storing and saving that data. What about if I'm taking all that small object files and combining it into one big file? So I can have, instead of having 1 million files of 60 byte, I can have one file of 0.06 gigabyte, which is approximately 60 megabytes, which can translate into 1 RPC, 2, 3 RPCs, and it really depends how the blocks then move across the network, but at least I don't create pressure on my server where I'm contacting the storage. So this is where I can get my improvement, and this is why the file size matters, because although the network can definitely support this stress, it means it might take some more time and it will take longer for us to get the information back. And that brings us to, once we understand that, that brings us to the next stage of detection and mitigation. And the first step of detecting is understanding where this situation can even happen. The first one is event stream. So when I'm combining the two worlds of microservices and big data analytics, I often need to understand how I'm capturing all these events. It's really great that I'm able to support huge scale with a huge throughput of events that comes from IoT devices, servers, applications, and all of that. But it's totally a different question how I support querying and analytics of that data at huge scale. And the reason for it is because the events themselves are often translate into kilobyte scale JSON during the ingestion procedure. And this is where we see the most cases and the most issues. In the ingestion part, where I'm building my Spark structure streaming to take that information and bring it back to the cluster, updating the format, etc. Sometimes when each batch is processing, each micro batch in my structure streaming is processing only one file, then it might be a problem, or only one small file, then I might have a problem. Second case where we see it is when we have over-paralleled Apache Spark job. So we know our Apache Spark, we have the executors and we have multiple tasks, and each read and write during the task might be writing their own files. Depends on the logic that we need, depends on how we define them. But if we have too many tasks processing a tiny percent of the data, then it means we might be in the stage where we have over-paralleled Apache Spark jobs. So this is the second case. The third case is having over-partitioned Hive tables. So this is another thought about how we are doing the granularity of saving these APIs called data, how we're saving these events. And a rule of thumb, if our Hive partition has less than 256 megabyte per partition, we need to check and reevaluate. Maybe we need to change the file hierarchy to make sure it works well with what Hive is expecting on that point. So we understand the cases. We went through three different prominent cases that we see in the industry. So what do we check when we are building our own infrastructure, or what can we check when we want to, in the existing infrastructures we already have? First one is data skew. Is my Hive partition file size smaller than what we mentioned before? Do I need to change the hierarchy? Do I need to maybe combine a couple of files? Second one, when looking at the Spark job writers in the Spark history server UI, I want to make sure what is the input, what is the output of the data, how much I'm reading, how much I'm writing, because this translates into small files. And the last one is the ingestion file size. This is when I'm combining the world of microservices and the world of big data analytics, and I want them to work together. Cool. So how do I mitigate? Like we mentioned before, file hierarchy. Define the source, the API type, and then specify maybe by dates. If 1 minute is too granular, you can make file for the whole hour. It really depends on the use case of the information, but this is another option to go with. When you're designing your partition, and this is probably the hardest part, you need to understand what the usage, who are the data scientists that are going to use it, who are the business analysts that are going to use it, what are the queries they're going to run, how they're going to use it, what are the different, if they have joins there, or if they have some filter operations there, how are they going to build their query? So having the design and the usage in mind can really help you when you define the partition. And there's no rule of thumb in there. Different companies build it differently, different data sources and different customers, data customers use it differently. Right, the third one is repartition versus coalesce. It's important to understand the difference. Repartition means I'm taking all my data and I'm repartitioning it. So it might be that I'm adding even more partition than what exists today. Not always I wouldn't want to do it always. Sometimes it will work, but sometimes, especially with small files, I don't want to introduce more small partition. I would actually want to have less partition. So it's important to understand the difference. And then we have the coalesce function. And coalesce does not introduce more partition. So this is a better function often to use. But again, according to your needs and according to the data and the queries and your customers. On Databricks, we have the auto-optimize. And with the auto-optimize, you can set up the properties to have optimize during the write and also optimize doing the auto compaction mechanism. So you can already set the Hive, the data warehouse that exists inside Databricks to constantly make sure it's optimizing the storage and the files underneath. The last one is the DeltaLake optimized performance. And the DeltaLake is a new storage format that was introduced a couple of years ago. Many of you know and use it and discussing it in the summit. And it brings multiple optimization that works well with Hive. The first one is compaction. So by using a mechanism named bin packing, it was able to compact the files into take a multiple small files and compact them into 1, 2, 3, 4, 5 files, depends on what exists there. The Z ordering is another technique that can help us combine information according to columns and according to when I know my column, when I know how my customer use the columns, I can specify the Z order. So it's a mathematical technique. Definitely, if it's relevant for you, try it out. And then we can define the target file size for Delta. So it will know in advance what is the minimum, at least what is the target. And then lastly, we have the file size for rewrites. So if you're rewriting any data, there's going to be some file size tune that we're going to tune for. Right, now it's the demo. Let's take a look at the demo.
To better understand how file format and file size affect the performance of querying and analyzing data, we're going to look into a simplified example of IoT data journey from transmission into data analytics. And today, this example is highly used in factories when they want to mitigate issues and save on expenses by attaching sensors that can help them later monitoring everything that happens in the factory, also make data-driven decision based on that by running some analytics and using tools such as machine learning to extract insights. And one of the prominent examples is valve monitoring and valve management, where we can collect events from all valves in the factory and later on analyze their behavior and what happened with them. This is the good side of the things. The challenging side is often results in a huge amount of data. And since we want to be able to respond relatively fast or to have ad hoc queries that run fast, we want to make sure our data systems is designed for it. So for this demo, I already mimicked IoT event data that is ingested into our system with structured streaming. And we're going to test out two different storage formats and evaluate how they work. So in the factory, imagine that I have my measure and control, and my measure and control is constantly sending events, telemetry stream into my analytics platform, into my data warehouse, where later inside the data warehouse, the data is being extracted, processed, organized, enriched with other enterprise data or external database in order for us to extract insights and run analytics on top of it. For capturing the telemetry for data analytics, you can use tools such as Apache Kafka, which is scalable and highly available as well. So it can really helps you capture high throughput of data. The challenge is each event can have its own small JSON file that is being captured. And to run the performance evaluation on these JSON files, we're going to mirror the data that was captured from tools such as Apache Kafka into Parquet format and Delta format. So in order to do so, I created two different Spark read streams and two different write streams. One of the writes is going to read the data and write it into Parquet, and the second one is going to write it into DeltaLake format. In the file itself, I have my events, my schema. It has event ID, it has event name, it can be failed or open or any of such, and I have event time. Very simple example of the data. Using Hive that is already built into my Azure Databricks environment, I'm going to create a new table from the Parquet location. So here I'm creating if not exist, I'm creating a database and I'm creating table 01, which is from a Parquet format, and I'm specifying the location. The second table is going to be a Delta table, specifying Delta format and location. And just to make sure there's no data duplication or no data got lost, I want to make sure they have the same amount of rows in each table. And I already know I generated 110 files, so there should be 110. And like you can see, there's 110 in the Parquet and in the Delta table. All right, now I want to see how long it takes me to query that table. So I'm going to run two identical queries that's going to select event name and event time. The only one thing that difference is I'm going to query that one. I'm going to run that query once from the Parquet and the second time from the Delta table. So running the Parquet one, and this one took me 1.56 seconds to finish. And now I'm going to run my Delta one, and that one took 0.90 seconds. All right, so the Delta one is already faster. I wonder if that's the case or there's something I can do about it. So for that, and you already know about it, we can use the Hive optimize command that helps me optimize the layout of DeltaLake Delta. So I'm going to use optimize and the Z order one. Let's run the Z order. Save some space and on the data. And let's see what's happening. Num of file added, 1, num of file removed, 101. So what happened behind the scenes, my optimized query combined a couple of small files into one file. And the couple of small files is actually 101 files that were removed in one file that was added. They're already addressing the issue of small files. All right. Can we optimize Parquet table file? I mean, is optimized query can run on Parquet? And unfortunately, the answer is no. Analysis exception, Delta table not found. It means it's only possible with the Delta format. I can run this optimization with the Delta format. Okay. So after I optimized, I deleted 101 files and I combined it into one file for my DeltaLake storage. Now I want to see if it even, if it made any change, what change in the performance wise. So Parquet table took 1.1 seconds and my DeltaLake table is taking 0.81 seconds. So yeah, definitely some change. Let's run it again and see what's happening. I know in the DeltaLake there should be, the caching mechanism should be kicked in at some point. So let's see what's happening with the optimization here. Yeah, absolutely. Definitely more prominent, 0.74 seconds. Yes, so running the Hive optimization by combining all these 101 files into one file and then adding the caching mechanism that Delta provide really helped with improving the run query. It's almost, yeah, it's half the time of what the Parquet query takes. So Delta table wins in our case.
Well, after we did this demo, we definitely see now how DeltaLake can be more efficient than Parquet and how we can leverage the Hive optimize command in order to combine multiple small files. So we've seen the problem, we understand why it happens, we learn how we can detect and mitigate, we learn about the three permanent scenarios where this happens. And I want to leave you with this quote that I think really represent everything that we do in the Data and AI Summit. So this quote is by Albert Einstein, and he says, "Intellectual growth should commence at birth and cease only at death." So I really hope you learned something new today. Always happy to chat and get your DMs over Twitter or over LinkedIn. Please feel free to reach out with any question, or if you want to share your experience with big data processing and big data analytics. Thank you.